Hello students, it is gravity time with Mr. Mabry, so I hope you are buckled in and ready to ride. Here's what this assignment looks like. This note page we're going to put into our science notebook. So what you need to do is pause this video, and why don't you go ahead and make 8 lines in your notebook. You don't have to make a box around it, but you can if you want. And what I'm going to do is take you through 3 different websites. This one, and this one. And we're going to explore the concept of what is gravity and how does it work in outer space. Once we have those websites explored, we'll have some statements written down, and then I will tell you how to do these drawings down here. But our hope is everything should fit on one single piece of paper. So, pause the video, make your 8 lines. Now we're getting started. First, we're going to head to my friend PHET. So if we click here, Gravity and Orbits, we're going to get a screen that looks like this, and we're going to head inside. So I'm going to go ahead and click play. Here we have the sun, and here we have our happy little planet, and here's the path we are taking in our revolution around the sun. Now, people like to think that this is what the Earth does because the Earth loves going in circles. The Earth is naturally a curvy driver. Well, surprise, folks. I'm going to take this thing we call gravity off, and I want you to see what the Earth's going to do. In T-minus 3, 2, 1. Sayonara, Earth. Pshhoom! You are going, gone! So this brings us to the first thing we know about the way objects move in outer space, and this is the first statement we are going to jot down, which is, left alone, objects travel in straight paths in space. But if that's true, if things really, let's clear this, let's reset, I think. Can we reset? Yep, let's reset. Let's start over. If objects travel in straight paths in space, then why in the world would it be going in a big circle? Well, let's talk now about this guy, Mr. Gravity. You can see gravity is being illustrated in this simulation by blue arrows. You can see a sun with a blue arrow and the Earth with blue arrows. And this goes to our first and most basic understanding of gravity. And that is gravity is a pulling force between 2 objects. Both objects are doing the pulling, but it is a pulling force. So, let's write that down. Statement number 2 is, wait for it, gravity equals a pulling force. Now, it's not, though, a pulling of equality between 2 different objects. So, even though this looks like the sun and the Earth are both pulling equally well, let's mess with something here. See where it says the mass of our sun is where it's supposed to be? What if we doubled it? Doubled it. So I'm going to slide this to the right. Notice, oh my goodness, the sun is getting, oh, wait, I didn't mean to. Let's do that again. Let's reset. So again, we have plane, happy Earth. There's gravity. There's our path. Maybe here's a little grid for you to watch. And notice the size of the arrow. If we increase the mass of the sun, then the pull gets bigger until, oh, that was a close call. Let's see what happens. Oh, it's a close call. So, big idea number 3. When you increase the mass of an object, either on Earth or in space, you increase the gravity. So let's go to our paper and type that in. The more mass an object has, the more gravitational pull it exerts on another. Now let's head back here. Let's try something else. Let's reset. Let's click play. Here's our path. Here's our gravity. Let's see what happens if I scoot the Earth a little bit. What do you want to do? Closer or farther away? What's that? Love it. Let's go farther away. Oh, whoa! What did the? You guys see these arrows? What's happening? I'm going to scoot the Earth out here. Put my little grid on, and let's see. Let's click play, and then, whoa, Earth! What are you doing? Huh? You're not orbiting the same. Your orbit looks a little bit different. In fact, Earth, where are you going? Earth, wait. Don't leave. Stop. I didn't mean it, Earth. Can I grab it? Oh, did I miss the Earth? Oh, let me bring it back closer. Don't leave me, Earth. Let's try closer to the sun. There, just, oh, too close. This brings us to statement number 4. The closer the distance between two objects, the more gravity they have. Or, if you want to state it succinctly, you would write, the closer the distance, the more gravity you have. Okay? So we're starting to see that gravity is an attractional force. The bigger and the more massive you are, the bigger the pull. And the closer you are to an object, the more pull you have. So this brings us to probably our most important statement is, and it's a long one, let's combine all of those things into a statement about what I like to call, for statement 5, the attraction tango. Attraction tango. That's right. Orbits are achieved when there's this perfect balance between size of the objects orbiting each other, distance between the objects, and how fast the object is going by itself. So that's why Miss Greaves and I like to call this the attraction tango. Because as they say in dancing circles, it takes 2 to tango. You have to have the right mass between both objects, the right distance between both objects, and the right speed of an object initially. To illustrate this, we're going to go to our second website. It's the NSTMF Lab, and it is super cool. So let's illustrate that. If I want to go into this lab and create my own universe, I can left click and hold here. And now I got a random object. But let's say I want to try to make something orbit around it. I'm going to left click, drag, and let go. Cool, I made something go around it. Look! I made a little sun and a little planet. Something with a lot of mass, so it's pulling on, and look, that's the orbit it got. That's its attraction tango. It's a little bit closer on one side, a little bit longer on the other. That's how all of the balance worked out when I created it. Let's see if I can get another one in here. Oh, too close. That didn't work. Let me try this again. Oh, is it going to be the same orbit? No, look, it's different. Let's zoom out a little bit. Look at that. I made a little solar system with 2 planets. Let's see if I can get one going out here. Oh, wait. No, you don't want to tango? Come back. Wait, wait, wait. It was going too fast. It couldn't achieve that attraction tango balance. Let me try a gentler one. Nice and slow. Nice and slow. Get sucked in. Come on. Yes. Got it. Of course, if I go too slow, let's see what this looks like. Uh-oh. Uh-oh. Not good. Not good. Not good. This is a really fun lab to play around with, creating different types of orbiting systems. I think you guys will have a lot of fun with this. But now, let's go to our final website, this YouTube video here. So I'm going to click on this, and I'm going to get a really old school video that's even older than me. Now, I'm not going to play all 5 minutes for you because you and I would both get sort of bored, but you can watch it. It's good. I'm going to jump to here. And here we're going to watch this lady tell these kids about, let's take the sound off. They're going to make this model of the solar system, and she's going to have this little ball in her hand. She's going to say, hey, let's pretend this thing is like a planet. And she's going to put it on this model of space and say, what happens when you just let a planet go in outer space? And you and I both aren't surprised. If you let a planet go, it just goes zoop in a straight line, like we've talked about. But then she said, hey, instead of assuming gravity is this magical force that just pulls, what if we change the way that we thought about space? What if we thought about space as a fabric? And if it's a fabric, like this black fabric, then maybe if we had a really heavy object, like a star or a planet, and we put that star or planet on the fabric of space, you could make a decent-sized dent. Bloomp. And this, though it's weird to think of, is what scientists say is the best way to think of gravity. Not a magical Yoda force, nor a baby Yoda force, but as a dent in what we call space-time. So, we're going to pause this for a second. We're not done, but we're going to write that phrase down before it escapes us. So our statement number 6 is, heavy objects put a dent in the fabric of space. So if we think of gravity in this way, then if we fast forward here to right about here, we're going to watch her model for us why planets orbit another. It's not magic, but see, as you put an object on there and it zooms around, it just circles because it's caught in the dent created by the object. And of course, the heavier the object, let's find her doing it again. Let's just repeat. There we go. And whoop, too fast. Come on, put it in, lady. Come on. Come on, Cletus. Put it in and zoop up to, okay, fail. You'll have to watch the video. So you make a dent, an object goes by and it gets caught spiraling around like a penny in one of those jars at a store. So we're going to write this down as sentence number 7, as the proper way to think of gravity working. Yes, it's a pulling force, but it's better thought of as a dent, and objects get caught in that dent as they spiral around it. What's really cool about that is, at the very end of the video, if you want to watch it in its entirety, you have this random dude shows up at 4:57 and he says, check this out. When we go out there beyond our solar system, we know that there are other planets orbiting stars because if your planet's big enough, watch the star right here. As planets go around, the star actually wobbles back and forth, back and forth. And that's what astronomers use to hypothesize that star in the night sky that's moving just a little bit is probably having a really massive planet close to it that's causing it to shift to the left and to the right. That's pretty cool. So our final statement is, large planets make stars wobble. This is how we detect planets outside our solar system. Once you have these 8 statements, why don't you go grab your highlighter and let's highlight the key 1 or 2 words in each of these. I think the key words here, we got straight path. Here, the key word is the definition for gravity. Statement 3 is all about mass. Statement 4 is all about distance. Statement 5 is about attraction tango. 6 is all about dents. 7 is all about orbits and dents. And then number 8 is all about making stars wobble. Now you guys have a useful note sheet. Okay, for the final part of your note page, you have to complete before you can submit this for credit. I now want you to draw out these first 5 statements at the bottom of your paper. What would these statements look like in pictures instead of in words? Like, for example, for picture number 1 here, maybe you want to draw, and I'm going to not be great at this. Is there? Okay. Maybe you want to draw a little circle here just with a straight line and call that little circle like Neptune or Earth or Comet. And to me, I see that, I'm like, oh, cool, you get, that's what we're saying. Objects in space travel in straight lines. So now that I've helped you out with the first statement, what do you think 2, 3, 4, and 5 would look like if you were to draw those statements instead of write them? I can't wait to see your drawings. Thanks for watching. Have a great day.